All right, so now that we've got our equation, let's go through and take the derivative of both sides with respect to time. So the derivative of volume would be 1, and it wasn't in terms of time, so we leave dv dt in there. The 1/12 pi, remember, is a constant, like 5. So if you had 5h cubed, you'd get 3 times 5h squared. So same idea. We're going to get 3 times 1/12 pi x h squared. So 3 times 1/12 would give us 3/12 or 1/4. And then h was not in terms of t, so we have to leave a dh dt in there. Now let's plug in what we know. We knew dv dt was 2. We knew h was 3, and the only unknown that leaves me is dh dt, which is what we wanted to find. So we can say 3 squared is 9. So 9 times pi times 1/4 would be 9 pi over 4. And to get dh dt by itself, multiply both sides by 4 over 9 pi, and then we can simplify. So we'll have 8 over 9 pi, and then we need to label that. So our numerator is going to be whatever h was in, and our denominator is going to be whatever t was in. So h was in meters, and time was in minutes. All right, so for our next one, example number 4, it says car A is traveling west at 50 miles per hour, car B is traveling north at 60 miles per hour, and both are headed for the intersection of the two roads. So at what time are the cars approaching each other when at what rate are the cars approaching each other when car A is 0.3, car B is 0.4 miles from the intersection? So here's the intersection of two roads. Car A is starting here, and he's coming west at 50 miles per hour. So x is changing at a rate of 50, and it is a decreasing quantity, so it would be a negative 50. If you didn't happen to recognize the negative at that point, it'd be okay. You could catch it later on in the problem. All right, then car B is traveling north at 60 miles an hour, approaching that same intersection. So this rate of change of this distance is going to be 60, and again, it's a decreasing quantity, so I could say that it's negative. And we want to know the rate of change of the distance between them. So I'm just going to draw a line that shows their initial distance, and then as they get closer, it'll be here, and as they get closer, it'll be here, and as they get closer, it'll be here. So we're looking for the rate of change of that quantity. So I'm going to call that z. That means we would be looking for dz dt. And we want to find it when they told me x is 0.3 and y is 0.4. If I know that x is 0.3 and y is 0.4, then I could find z. If I didn't happen to think to do it right here, the problem would prompt me to do that a little later on. But if I go ahead and notice, this is 0.3, this is 0.4, this would have to be 0.5, right? 3, 4, 5 triangle. So I'm going to look at, are any of these quantities constant? Well, no, this distance is changing. It's getting shorter and shorter as we go. This is changing. It's getting shorter and shorter, and the distance between them is getting shorter and shorter. So I don't have any constant values, so I'm going to differentiate first. So we have done this exact same differentiation earlier today in a previous example. Derivative of x squared is 2x dx dt. Derivative of y squared is 2y dy dt. We just had a constant on the other side when we did it with the latter problem. So in this case, we will have z squared, so the derivative of that would be 2z dz dt. So let's go back and plug in what we know. We know that x is 0.3 and that dx dt is negative 50. We know that y is 0.4 and dy dt is negative 60. And so here is where, if I had not gone ahead and found z, when I get here and I still have z and dz dt left, and I know I'm supposed to be finding dz dt, that's where it would prompt me to go, there's got to be some way I can find z in this problem. And so I would go back and say, okay, if I know x and y, I could find my z value. So I could plug in z, and then my only unknown is dz dt, and that's what I'm trying to find. So if we simplify, 2 times 0.3 times negative 50 and 2 times 0.4 times negative 60, combine those values, we'll get negative 78. And my answer is going to be in whatever z was measured in over whatever t was measured in, which is miles per hour. Now, if you did not happen to recognize these negative quantities as you were going through the problem, when you get to the very end down here, you could either say, hey, this distance between those two is a decreasing quantity, and then add your negative in, or you literally could just say the distance between them is decreasing, either one. All right, example 5, last one that we're going to look at for today. For example 5, it says a man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? And they were kind enough to give us a picture so that we could see what they're talking about. Here's my searchlight. Here is a constant value of 20. Nobody's picking up the searchlight and moving it. Nobody's picking up the path and moving it. So that 20 is a constant value that I am going to put in before I differentiate. What they said is that the man is walking along this path right here, and as he does, the searchlight is rotated through this angle theta to follow him along that path. So it said that he walks at a speed of 4 feet per second. So the rate of change of this distance or this length right here, that rate of change is 4. And it says the searchlight is 20 feet from the path. We've already discussed that. At what rate is the searchlight rotating? So I want the rate of change of this rotation of that angle. So that would be the rate of change of theta when the man is 15 feet from the point on the path closest to the searchlight. So here's the point on the path closest to the searchlight. He's 15 away from that. So that would be when x is equal to 15. Now, if I know that x is equal to 15 and I know that this quantity is 20, Pythagorean theorem would enable me to figure out that my radius is 25. And again, if I didn't think to do it here, then I would be prompted to do it later on in the problem. But we're going to go ahead and throw it in here since we've seen that several times now. We might be more apt to do that when we see it. So I need to create an equation that is going to relate theta and what is opposite to it, x, and what is adjacent to it, 20. Well, opposite and adjacent is tangent. So I could say, okay, the tangent of theta is going to be x over 20. If I multiply both sides of that by 20, I'll get x is equal to 20 times the tangent of theta. So there's my equation. We had said that 20 was a constant value, so it should be plugged in before we differentiated, so that's why we've done that. So now let's take the derivative. So the derivative of x is 1, and it wasn't in terms of t, so we leave the dx dt. The derivative of tangent is secant squared, so we'll have 20 secant squared. And theta was not in terms of t, so we leave a d theta dt. So now we can plug in what we know. We know that dx dt is 4, and we need to find secant. Now remember, secant is the reciprocal of cosine, right? Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So if I come over here, my hypotenuse r, here's where I would be prompted to find that if I had not already, but we already found it to be 25. So hypotenuse over adjacent would give me 25 over 20. So I'm going to simplify that down to 5/4. So there's my secant squared. And then d theta dt is what I'm trying to find. So 5 squared is 25 over 4 squared is 16. Multiply that by the 20 and simplify it down, and we'll have 125 over 4. And then multiply both sides by 4 over 125. And we want to give our answer in whatever theta was measured in over whatever the time was measured in. Unless they tell you degrees, always assume radians. And our time was in seconds.